Welcome to lecture number 2, Oxford Principle of Flight, chapter number 4, Subsonic Airflow, produced by Aviator Cloud. In this chapter, we will discuss about aircraft terminologies, basics of airflow, two-dimensional airflow, pressure distribution, center of pressure and aerodynamic center, pitching moments. All are very important concepts, and you will have to remember these concepts for a lifetime as long as you stay in aviation. So first, what is an aerofoil? An aerofoil is a body so shaped as to produce aerodynamic reaction normal to the direction of its motion through the air without excessive drag. क्या बोल के गया? कुछ समझ में आया? So a body so shaped. So first it is a body so shaped, okay, to produce aerodynamic reaction. Let's say it produces aerodynamic reaction normal to the direction of the motion. So if the direction of the motion is like this, so it will be normal to this through the air without excessive drag. So this is the Chatur style, right? Chatur style definition. So I can give you a Rancho style definition, which is very simple. It is a shape capable of producing lift with relatively high efficiency. So what is an aerofoil? An aerofoil is a shape that can produce lift. Very simple. Okay, both are correct. So if you can remember, it is very good. What is an aerofoil? An aerofoil is a body so shaped as to produce aerodynamic reaction. So aerodynamic reaction, in other way you call it lift. Okay, so a body which is so shaped that can produce lift, that means produce aerodynamic reaction normal to the direction of its motion. It is normal to the direction of its motion, actually, for the normal to the relative airflow through the air without excessive drag. Okay, fine. So basically, for understanding, you need to know an aerofoil is such a shape of the aircraft wing which can produce lift. Very simple. Now we will understand there are a lot of things in an aerofoil. Okay, lot of things. So first is a chord line. Chord line. What is a chord line? A chord line is a straight line. See this yellow line. Okay, the chord line is a straight line joining the centers of curvature of the leading and trailing edges of an aerofoil. So basically, a chord line is a straight line which connects the leading edge and trailing edge of the aerofoil. So joining the leading edge and trailing edge by a straight line. So what is the first criteria of an chord line? It is a straight line. Understood? So what is chord? The distance between the leading and trailing edge measured along the chord line. So basically, chord is the distance between leading edge and trailing edge. So every definition is important whenever we will study in the later concepts. These definitions will come into play. So chord line is very simple. Next, angle of incidence. The angle between the wing root chord line and the longitudinal axis of the aircraft. So chord line and the longitudinal axis of the aircraft. So let me draw it first, then I will explain you. Let's say this is an aeroplane Okay, this is the wing. I am very bad in drawing, so please bear with me. So this is an aeroplane. Now the wing of the aeroplane, if I draw a little bit more, let's say the wing of the aeroplane, I mean the cross section of the wing like this, and this is the longitudinal axis of the aeroplane. So if we call it, the longitudinal axis of the aeroplane goes like this. Okay, this line along the longitude of the wing, along the longitude of the aeroplane, this is the longitudinal axis of the wing. And what is it saying? And wing root chord line. So I need to draw a chord line from here to here. Okay, straight line. So this chord line and the longitudinal axis is making an angle here, theta. Okay, theta. If you can imagine this diagram, all your definition will be easy to remember. So this theta is the angle of incidence. There is something called angle of attack. I am not attacking you with that. Okay, this is angle of incidence. So what is that? If I may explain again, the longitudinal axis of the aeroplane. So this is the longitudinal axis of the aeroplane. That means this is the aeroplane. Let's say this is the aeroplane. So the longitudinal axis of the aeroplane goes like this. Am I correct? So this red line, suppose this is the red line, longitudinal axis. Now here you have the wing over here. Here you have the wing, right? So this wing, if we cut it cross section, so this wing can be shown like, let's say this is the wing. Now we know what is a chord line. We know the definition of a chord line, connecting the leading edge and the trailing edge by a straight line. Now this straight line, the chord line and the longitudinal axis of the aeroplane is cutting over here, which is theta, which is angle of incidence. So is it a fixed line or it is a variable line? What do you think? You can comment, okay? Fixed line or variable line. So it is a fixed line for an aeroplane. Okay, main wing, fixed line, because the longitudinal axis of the aeroplane cannot change, and the chord line also generally doesn't change of the wing. Okay, so this angle is fixed for the wing. It may variable for the tailplane, horizontal stabilizer. Yes, it can vary for the tailplane. I will explain later, because what happens to the tailplane? Here you have the tailplane, right? Now this tailplane we can rotate little bit, okay, up and down. So when we change the tailplane, then the angle also changes. The chord line changes the angle between the longitudinal axis and the chord line of this aerofoil. Okay, tailplane aerofoil, tailplane aerofoil. The angle can change. That's why it can be variable. So just to remember, the axis is fixed. The angle is fixed for the wing, for the main wing, and it can change for the tailplane. The most important thing is to understand the angle of incidence. I say again, it is the angle between the wing root chord line or the chord line and the longitudinal axis of the aircraft. This is very simple. So what is a main line or cable line or mean cable line? Okay, so mean cable line is a line joining the leading and the trailing edges of an aerofoil. So connecting the leading and trailing edge of an aerofoil. If this is an aerofoil, so this is the leading edge and the trailing edge, but there is a catch. Equidistant from the upper and lower surface. So equidistant from the upper and lower surface. So I need to go in between the two surfaces which will be equidistant, right? So this line is equidistant. So what is equidistant? So distance from here and distance from here will be same. Okay, h. Distance from here will be same. Similarly, distance from here and here same. Okay, so it is a line that connects the leading edge. This is leading edge, this is trailing edge, connecting these two, and it is equidistant from the surface. So my question is the camber line, mean camber line, is a straight line? Straight line? Yes or no? You can comment. Answer is no. The camber line is not a straight line. Chord line is a straight line. Chord line is a straight line, but camber is not a straight line. This line represents the curvature of the wing. So what is the importance of this line? If I draw a camber line like this, you will understand how much is the curvature of the wing. You will be able to understand, how much is the curvature of the wing. So this is main camber line. Maximum camber. What is maximum camber? The maximum distance of the main line from the chord line. So maximum distance from the main line or the main camber line. So this main camber line is the red line. Okay, this is the camber line. Because it is equidistant. You can see this is equidistant from the upper and the lower surface of the wing. So this is the main camber line, and chord line is the straight line connecting the leading edge and the trailing edge, right? So where the maximum distance, so let's say the maximum distance is here. Okay, here the both has a maximum distance. So this is called maximum camber. So this portion is called maximum camber. So what is the definition of maximum camber? The definition of maximum camber is the distance where the distance is high between the chord line and the main camber line. Okay, now here comes a question. If the aerofoil is symmetrical, so like this is symmetrical. Okay, symmetrical. So if the aerofoil is symmetrical, what will happen to the chord line and the camber line? So chord line and the camber line. So first draw the camber line. So you see the camber line will be equidistant from upper surface and the lower surface. So equidistant from the upper surface and the lower surface of the wing. And chord line is the straight line connecting the leading edge and the trailing edge. So in this case, the camber line will also be a straight line, and both lines will superimpose to one another. Say in a symmetric aerofoil, the chord line and the camber line, look at here. In a symmetric aerofoil, the chord line and the camber line are co-identical, or there is no camber. So MCQ can come in a symmetrical aerofoil. What is the camber? Is it positive camber? It is negative camber? It is no camber, or cannot determine? Okay, so we didn't discuss the positive camber and negative camber. What is positive camber? Positive camber is the camber line lies above the chord line. So you know chord line is the baseline always. Okay, chord line is the straight line. If the camber line lies above the chord line like this. This is positive camber. Positive camber. Negative is when the camber line lies below the chord line. So if the camber line is like this, below the chord line, it is negative camber. Negative camber. So MCQ question will come. For a negative camber, option 1, camber line lies above the chord line, camber line lies below the chord line lies above the camber line, like this. So how to remember this? Always remember this yellow line is the chord line. Yellow line is the chord line, and chord line is always straight line. Okay, and straight line, and it is the baseline. So somebody is above it, somebody is below it. By chord ratio, the maximum thickness or depth of an aerofoil section expressed as a percentage of chord. What does that mean? It means for an aerofoil, the ratio is equal to thickness divided by chord into percentage, okay, expressed in percentage. So thickness is the maximum distance between the upper and lower surface. Let's say this is the wing. Okay, where is the maximum distance between the upper and the lower surface? Let's say it looks like here is the maximum thickness. Okay, maximum thickness, we call it T max, maximum thickness. And let's say chord is, where is the chord line? The chord line is here. Actually I have made the wing, sorry, not this one, let's say this one. I have made the chord wing very curved. So this is the chord, okay, this is the chord C. So ratio will be T max divided by C into percentage. Okay, so for an example, this is not required, but I am giving an example for better understanding. Let's say maximum thickness T max is equal to 0.12 meter. Okay, that means this one is 0.12 meter. Chord C is, chord length is 1 meter. So what will be the percentage? T by C ratio in percentage will be 0.12 divided by 1.0 into 100% is equal to 12%. Okay, so thickness by chord ratio is 12%. What does that signify? It includes the location as a percentage of chord aft of the leading edge. What is the significance? The thickness and thickness distribution greatly influence the airflow characteristic of the aerofoil section. So mainly we just need to know about the definition, and also remember it is calculated in percentage. Leading edge radius. Definition: the radius of curvature of the leading edge. So leading edge, the radius of curvature. So let's say if this is the curvature profile, this one, so how will be the wing? The wing will be like this, let's say like this. Okay, so this is the leading edge radius. So it defines how sharp the wing is, or how sharp, I mean how much will be the width of the wing. If the leading edge radius is very small, so it can be, or it will be, a sharp wing. Okay, sharp wing. So for supersonic aeroplane, this leading edge radius is low, and for our civil aviation aircraft, leading edge radius is high, and it can fly at a lower speed. So this is the understanding of leading edge radius. Importance: the size of the leading edge radius significantly affects the initial airflow characteristics of the aerofoil section. Relative airflow. The relative airflow, it is the direction of airflow produced by the aircraft moving through the air. So direction of airflow produced by the aircraft moving through the air. What does that mean? Let's say this is the aircraft. This aircraft is going to this direction, right? So if it is going this direction, there are a lot of molecules over here, air molecules. So when the aircraft is moving at a speed, all these molecules, let's say it becomes the straight line of airflow, this one. So this straight line of airflow, which is not affected by the aircraft wing. So here it is affected. We are not considering this area. We are not considering. We are considering this area. The airflow of the opposite side is the relative airflow. Okay, so it is basically the airflow that is opposite, I say again, that is opposite of the direction of the aircraft. Okay, so this is a relative airflow relative to the aircraft. Now if the aircraft is, let's say, climbing, how will be the relative airflow? Now if the aircraft is climbing like this, the nose up attitude, but what is the flight path? Now here you have to remember, it is not related to the attitude of the aircraft, it is related to the flight path of the aircraft. Flight path, F-L-I-G-H-T, flight path. What does that mean? This aircraft is climbing to this direction, so flight path is, let's say, like this. Attitude is also similarly to the upward. So the relative airflow will be opposite of the flight path. Here is the relative airflow. Here is the relative airflow. Okay, so relative airflow is always opposite of the flight path. So the direction of the aircraft is moving. Now if this aircraft is descending, where is the flight path? The flight path is like this. It is descending. So relative airflow is always opposite. Okay, so you have to consider the flight path. Now you can see this image. This can be little bit confusing. Where is the aircraft nose pointing and where is the flight path? Now this aircraft, for some reason, it can move like this. Let's say this is the attitude. Here is the attitude is towards upward, but the flight path of the aircraft can be like this. It can go like this. Okay, so here the aircraft is moving like this. So the flight path is like this only, this direction only. Nose is towards somewhere else. Okay, so where will be the relative airflow? The relative airflow will be opposite of the flight path, right? Opposite of the flight path. Also it should not be affected by the wing. Relative airflow has three qualities. One is the direction. It is parallel and opposite to the flight path of the aircraft. So if the yellow line is the direction of the flight path, the blue line, the relative airflow, will be opposite direction and also parallel to the direction of the flight path. Condition number 1. Condition number 2. Condition: air close to but unaffected by the presence of the aircraft pressure, temperature, velocity. That means the air that is very close to the aircraft, the direction of the airflow. Okay, that is the relative airflow. Whenever the air reaches to the body of the aircraft or to the wing, it can be affected by pressure, velocity, temperature. So that is not being considered. So this condition has to be fulfilled. And magnitude, the true airspeed. So this airspeed is considered as TAS, true airspeed. I hope you already know about what is TAS in your navigation. So these three conditions are important. MCQ question may come from here. As air flows towards the aerofoil, like this, air is coming towards the airfoil, it will be turned upward to the lower pressure area, okay, of the upper surface of the wing. So air is coming like this, it is going upward and it is going to the lower pressure area, upper surface of the wing, and after passing the wing it is again going down. So now this is called, when the air is going up, it is upwash, and this is downwash. What is angle of attack? Angle of attack is the angle between the chord line. So chord line is here, the chord line of the wing, and the relative airflow. So let's say this is the relative airflow, and the chord line. So this angle is the angle of attack. Remember, it is always with the angle between the relative airflow, not the flight path. So flight path or not the nose of the aircraft, okay, it is always with the relative airflow. So what is angle of attack? The angle of attack is the angle between the chord line of the wing, and the relative airflow. So in this chapter number 4, some images are there. Understanding this diagram is very important. So figure 4.4, what it shows an aerofoil section at a representative angle of attack. Let's say whatever angle of attack, 4 degree. Already you know what is angle of attack. Subject to a given dynamic pressure. If the static pressure on one side of a body is reduced more than the other side, a pressure difference will exist. So you see here it is minus, here also it is minus, right? This is plus. What does it mean? So let's say this aircraft is moving, right? So the air is coming like this. So when the air is coming, you know about upwash. Because of upwash, this air is going over the wing, and for downwash it is going down, right? Some air is coming like this and it is going below the wing, okay. So what is happening? There is some molecule, there is still some air which is coming and hitting at the leading edge radius, right? It is hitting on the leading edge. So you see when the air is coming like this, so it has a dynamic pressure half rho v square. So when at a v it is attacking over here, so a dynamic pressure is building up. So this is a positive pressure, that's why it is plus, okay, that's why it is plus. Now you see whatever the aerofoil you have, this is your aerofoil. Now your aerofoil is more curved to the upper wing and less curved to the lower wing. So as it is more curved to the upper wing, already from the previous lecture you know that from the Bernoulli's principle, P plus half rho v square is equal to constant. So you know airflow over the wing is increased, that's why static pressure will decrease. So the static pressure decrease is shown as minus, okay. Now below, earlier we knew that below the pressure is more. No, now the below also the same phenomena happens. That means P plus half rho V square. Here also the air is moving faster, but not as fast as it is going from the upper side. So here also the pressure is reducing. The static pressure here also below the wing is also reducing, but the reduction is less than here. Okay, so what is happening? We are having positive pressure over here at the leading edge. Okay, and we have negative pressure at the upper surface of the wing. Also we have negative pressure at the lower surface of the wing also, but the difference of the negative pressure, the static pressure, let's say here the static pressure is 5, here the static pressure is, let's say, 10. So I mean a drop of static pressure. So here static pressure is more or less. That is why this upward force will exist, what we will call lift. And already we know that lift, okay, that we'll discuss later. Now what is happening here? You see, now half rho V square is the V, that the velocity, right? Now if your aircraft is moving faster, that means higher IAS, indicated airspeed. So if it is moving more at a high speed, what will happen? The flow of the air will be more, the molecule heat will be more. So you see this positive pressure over here will be bigger. Also, because of the more V, half rho V square, your dynamic pressure is more, so your static pressure your drop will be more drop of static pressure. Here also static pressure drop will be little bit more, not very much, little bit more. So this is why you see this curve, this lift curve. This is not lift curve, but the low pressure area, this is very high compared to the previous one. So this is the image that wants to explain, let's say 4.5 figure. It shows the same aerofoil section at the same angle of attack, but subject to a higher dynamic pressure. That means a higher IAS. If the dynamic pressure IAS is increased, the pressure difference will also increase. These two lines you have to remember by heart. Okay, a lot of MCQ will come. If the static pressure on one side of the body is reduced more than the other side of the body, the pressure difference will exist. Number one. Number two, if the dynamic pressure is increased, the pressure difference will also increase. Your MCQ may come like this: if the dynamic pressure is increased, the pressure difference will, number one, decrease, number two, remains same, number three, increase. Okay. Now most of the students do not read these pages. They think this is unnecessary, but it is very, very important. You have to read these pages at least 5 to 10 times. Influence of angle of attack at a constant dynamic pressure IAS. Increasing the angle of attack up to 16 degree will likewise increase the pressure differential, but also will change the pattern of pressure distribution. We need to understand the change of the pattern of pressure distribution. What is this pressure distribution? Okay, let's say come to this image. Now this image, this red line, already we discussed this red area. I forgot to mention the point where the molecule is coming and hitting, okay, directly, and it cannot neither go up nor go down. Okay, this point is called stagnation point. Remember, stagnation point. Okay, this is a point where the airflow, some airflow will go from the above, some airflow will go below, but some airflow will hit at a point where it can neither go up nor go down. So it will become the stagnation point. Understood? And important, the pressure at the stagnation point is static plus dynamic. So at the stagnation point, the pressure is static plus dynamic. Okay, MCQ question. The pressure at the stagnation point is static only, dynamic only, static plus dynamic, static minus dynamic. Okay, this kind of MCQ comes. Anyway, so now in this image, let's say this aircraft wing, let's say we zoom here. Okay, now this is the cross section area of the wing, aircraft wing. This aircraft is going like this, nose is like this, but let's say it is the flight path is this way. Okay, so nose down, let's say it is going like this. So what will happen to the relative airflow? The relative airflow is opposite of the flight path. This is the relative airflow. Now this relative airflow is this black line. Okay, this is the relative airflow, direction of the relative airflow on the wing. Now where is the chord line? Check the chord line. This is the chord line, right? This is the chord line. Now this chord line and this relative airflow is making an angle which is 4 degree minus 4 degree. Why minus? Because you see the relative airflow is above the chord line. Okay, this is why it is minus. Now already you know this about this stagnation point and this dynamic pressure half rho v square here. That is why some positive pressure is happening over the leading edge. The air that is going above the wing, so the static pressure is reduced here above the wing. Also some air is going below the wing and here also the static pressure is reduced. But this minus 4 degree is so important, where the static pressure below and the static pressure above, the reduction of static pressure is same. So if the reduction of static pressure is same, that means there is no difference of static pressure below and above. So there will be no upward force. So there will be no lift. So what is important? It is important to know that minus 4 degree angle of attack is called no lift angle of attack. Okay, MCQ will come. No lift angle of attack is, what is the value of no lift angle of attack? MCQ minus 4 degree plus 4 degree minus 8 degree plus 8 degree. So you have to remember minus 4 degree is no lift angle of attack, and this is the pressure distribution scenario between above and below the wing. What will happen if the angle of attack is 0 degree? Now at 0 degree, okay, compared to the free stream static pressure, there is a pressure decrease over the upper surface. So there is a static pressure decrease over the upper surface and also at the lower surface also. But the pressure decrease at the upper is more decrease, and here it is less decrease at the below. So for a cambered aerofoil, there will be a small amount of lift at small negative angle of attack. That means minus 4 degree to 0 degree. So at 0 degree, we are getting some lift. Okay, so there is a misconception that we think that at 0 degree angle of attack we will not get any lift. This is wrong because you have a cambered aerofoil. Okay, if the aerofoil is not cambered, that is a different scenario, but we are taking a cambered aerofoil. You already know what is a camber. Anyway, so 0 degree angle of attack, we are getting some lift. So don't take this misconception. Now what will happen if the angle of attack is positive, plus 4 degree? So from 0 to 16 we will get the good lift. Okay, so increasing the angle of attack increases the lift force because the acceleration over the air of the airflow over the top surface increased. So what is happening? At 4 degree, the airflow over the top surface is increasing. That means the more the angle of attack is increasing. If your angle of attack is increasing, so airflow above the wing is also increasing. Okay, so if the airflow increases, then more upward force will be generated. That is the thumb rule. The reduced pressure peak moves forward as the angle of attack increases. Now this is important to know. You see something called peak over here. What is a peak? You see the shape. Look at the shape. The first shape was like this. Okay, come here. You see 0 degree, your peak of the pressure curve. If this is the pressure curve, okay, this pressure curve is like this. Okay, as your angle of attack is increasing, now the pressure curve is more stiff, like this and like this, right? So this peak is moving. Earlier this peak was here, here was the peak. Now the peak has been moved forward, little bit forward. Okay, so what is happening? The reduced pressure peak, this is called reduced pressure peak, moves forward as the angle of attack increases. Very important concept and very important MCQ also. If your angle of attack increases, the reduced pressure peak slowly moves forward. When your angle of attack is 8 degree, that means more. So your peak is also moving more forward. Okay, forward. So peak is also moving forward. Also, to understand that your stagnation point, earlier your stagnation point was here. Look at here. Look at this diagram. Let me draw it with yellow. Earlier your stagnation point was here. Okay, as your angle of attack is increasing, now your stagnation point is coming below, little bit below the wing. Okay, then when your angle of attack is more increased, your stagnation point is coming more below the wing, and you see this area, this red area, this stagnation area is slowly going down. Okay, so what will happen at 14 degree angle of attack? 14 degree is a very good angle of attack, where we are getting the greatest pressure drop above the wing. And you see your shape is coming like this, and your peak is almost the forwardmost point. This peak is pressure drop peak. Okay, pressure, that means here the pressure is already the minimum. Okay, pressure drop peak. This is pressure drop peak. Now what will happen at 14 degree at the below? Now you see this positive pressure red area has already covered the lower area. Okay, so that means here already we are getting positive area, positive pressure. So lift, we are getting very good amount of lift, because here almost it is positive and here it is the negative, most negative, that means the lowest one. So we are getting very good positive pressure, very good amount of lift. Okay, but what happens at angle of attack higher than the approximately 16 degree? Let's say this is 16, or let's say approximately higher than 16. The extremely steep adverse pressure gradient prevents air that is flowing over the top surface from following the aerofoil contour and the previously smooth streamline will now separate. So see, the higher that angle of attack, as you increase, you are getting more lift. But above 16 degree, what will happen? This airflow that is coming here, it has to upwash. It has to go a very high upwash, right? And it has to go. But what happens? The airflow breaks down here. Okay, it is a stall. We will discuss in the stall section. But what will happen now? This airflow over the wing is turbulent, and that is why we are not getting any low pressure area above the wing. Low pressure area we are not getting above the wing, but high pressure area we are getting below the wing anyway, more than 18 degree. 16 degree. So we are not getting any lift. Okay, so we'll discuss this later. So why I I took so much time explaining this. You need to understand few things, which are, you need to understand the pressure pattern as your angle of attack is increasing, and also two important things, that what is zero lift angle of attack? This is minus 4 degree. What is at 0 degree angle of attack, does the wing produce lift? If it is a cambered wing, yes, 0 degree also it will produce some lift. 4 degree, 8 degree, 14 degree, what happens as the angle of attack increases? Your low reduced pressure peak slowly moves forward. Okay, the peak move forward. So 2-3 things that you need to carry from here. So now we will learn a very important concept, which is called the center of pressure. Now, as you know from the previous diagram, that as the angle of attack increases, the reduced pressure drop, okay, the reduced pressure drop peak moves forward, right? Peak moves forward. So as the pressure drop peak moves forward, so your upward force, or we call it lift, that force will be higher. High force will be moving forward, right? So this line from here, it will go from here. So for our assumption, for our calculation, so lift is produced everywhere, right? Above the wing, it is produced, but the maximum wing is being produced at a point where the peak is there, pressure drop peak is there. So for our calculation, for easy, to make our calculation easy, we consider, okay, that my lift is producing from here. Okay, so lift is producing from here. So this point, for our calculation, this point we are calling CP, center of pressure. Center of pressure. Okay, so lift is being produced through the center of pressure. This is we are considering. So MCQ will come, lift is produced at the center of gravity, no. Center of pressure, yes. Okay, now the movement of the center of pressure, as you have already learned, if the angle of attack is increased from minus 4 degree to 0 degree to 8 degree plus 8 degree plus 14 degree, as the angle of attack is increasing, this center of pressure will also move forward. Okay, move forward. That means earlier the CP was here, now the CP has been moved here, moving forward. So as the angle of attack increases from 0 to 16 degree, the upper suction peak moves forward. Yes, we know. So the point at which the lift is effectively concentrated, the CP, or the center of pressure, will move forward. Very good. The CP moves forward and the magnitude of the lift force increases with increase in angle of attack. Yes, as the angle of attack increases, the magnitude of the lift increases, because the low pressure, more low pressure above the wing, until the stall is reached, when the lift force decreases abruptly. Okay, Note that the CP is at its most forward location just before the stall. Stall means turbulence of airflow, no lift is stall. Okay, we'll discuss later. So if we see this graph, what happens? Let's say this is your wing, right? This is your wing. Now in this wing, where is your initially, where is your let's say CP? Let's say your CP is here. Okay. Now as your angle of attack is increasing, your CP is moving forward. So now this red line, see, this is CP position percentage chord aft of leading edge. So percentage of chord, already you know the chord line. Let's say this is 100% of the chord from aft of leading edge. So let's say you are here, your CP is here, just for example, just for imagine. Now as your angle of attack is increasing, your CP is moving like this. You see angle of attack, this line is angle of attack. Let's say this is 0 minus 4 degree, this is 0 degree, plus 4 degree, plus 8 degree, plus 14, plus 16 here. So your angle of attack is increasing and your CP is moving forward. Here, let's say at 16 degree, what is happening? You are here, your CP is at the forward most position and maximum lift you are getting. Okay, this is your CP. Now above 16 degree, suddenly your because of turbulent airflow, stall happened and no lift is there. Now your CP will suddenly go back again and no lift. That's why this curve, that's why this line, okay, suddenly it will go to the back. So this is the movement of the CP. So what to carry from here? To carry from here is the maximum lift. Okay, the maximum lift, where the maximum lift is produced, the CP is at the forward most position. Okay, so maximum angle of attack. So what is happening? Note that CP is at its most forward location just before stall. If stall happens, then CP will go back. Another very important concept, aerodynamic center or AC. Now aerodynamic center or AC is a point on the chord line, okay, which is approximately 25% of the chord line. It is a point. So what does that point do? Now this point, let's say it is between the normal range of angle of attack, which is, let's say, 0 degree to 16 degree. Normal range of angle of attack, this is a fixed point. This point will not change, where the lift will change. This lift force will change, right? If the angle of attack is increased, let's say this lift force will increase. Also we know that CP position will move forward, okay, but with respect to this aerodynamic center, the momentum will remain same. What does that mean? Let me explain. To simplify this, let's say this is your aerodynamic center, which is a fixed point, right? This is a fixed point. Now let's say you have alpha 1 angle of attack over here, alpha 1. For example, you have angle of attack 5 degree, okay, alpha 1 5 degree angle of attack, and you are producing a lift of, let's say, 5, okay, let's say 5 Newton, okay, 5 Newton lift you are producing, just for example, and your CP position is here, CP point is here, and the distance between AC and CP D1 is equal to, let's say, 4 meter, okay, 4 meter. So aerodynamic center is a fixed point. Now what is your momentum? Your momentum is 4 multiplied by 5 is equal to 20, for example 20, okay, 20. Now, as your angle of attack is increasing from 5 degree, your angle of attack is increasing to 10 degree now. So, if angle of attack is increasing, your lift force will increase. So, your lift force, you see this line, lift line, the length of the line has been increased now, L2. So, your lift force has been increased, and now you have, let's say, produced 10 Newton of lift. But side by side, your CP position from here, it has been moved forward. Already you know, as the angle of attack increases, CP moves forward. Very good. Now your CP has come here. So what has become D2, the distance between AC, aerodynamic center, and CP, this D2 now has become 2 meter. Okay, 2 meter. So what will be the momentum? It will be 2 into 10 is equal to 20. So now you see, the earlier this momentum was 20, now also the momentum is 20 because of this fixed point aerodynamic center. So aerodynamic center is a center where whatever happens, angle of attack increases, decreases, CP moves forward, backward, whatever happens, this momentum is always same. Okay, and it is basically, it is 25% of the call point. Remember this, it is 25% of the call point. Here it is 25% of the call point at lower speed. Okay, we'll discuss this later in later chapter number 10. Now let's understand the pitching moment for a symmetrical airfoil. Now, what is a symmetrical airfoil? Symmetrical airfoil is an airfoil where the upper surface of the wing and below surface of the wing, the curvature is same. Okay, and already you know, symmetrical airfoil, the chord line is, this is the chord line, already you know. Also you know, the camber line also is the same line. Okay, it is also a straight line. So chord line is a straight line, you know, camber line is a straight line, you know. Okay, symmetrical airfoil. Now what happens in symmetrical airfoil? The pressure distribution with angle of attack for the symmetrical airfoil 4.11, when at 0 angle of attack, let's say this is 0 degree angle of attack, the upper and lower surface forces are equal and located at the same point. So upper surface, here the pressure distribution and lower surface pressure distribution is same. So there will be no upward force or downward force because the pressure reduction in both is same. So it will produce no lift, right? And CP position, let's say CP position is also here. So what is saying, with the increase in angle of attack, now let's say here the angle of attack is increased, the upper surface force increases while the lower surface force decreases. So upper surface, yes, upper surface, the low pressure area has been like this, and lower surface like this. So what happens, there will be an upward force. Now this blue line is bigger. You see this blue line, this blue line is bigger. Earlier this blue line was same, length was same. Now this blue line has been bigger. A change in magnitude of it has been taken place with no change in the CP position. Now what happens in this is very interesting for symmetrical airfoil, the CP position does not change, CP, I'm not talking about AC, aerodynamic center, I'm talking about CP, center of pressure, where the lift is produced. That CP position also does not change in a symmetrical airfoil. Remember, this is the characteristic of a symmetrical airfoil. Thus, the pitching moment about the aerodynamic center for a symmetrical airfoil will be 0 at normal angle of attack. Very important MCQ question. For a symmetrical airfoil, what will be the pitching moment about the aerodynamic center? So option 0. Answer is 0. Okay. One of the big advantage of symmetrical airfoil. So remember these lines and go and read your books. The more you read your textbook, the better you understand aerodynamics. Okay. Now summary of the chapter, what already we have discussed. Airflow pattern, ultimately lift and drag will depend upon the angle of attack, which is a subject of the airflow cross-sectional area change. What is aerofoil shape? We discussed about thickness, we discussed about camber. Airflow cross-sectional area change we already discussed. Air density, mass flow of air decreases with increased altitude, already we discussed in lecture number 1. Okay. Now velocity, mass, airflow changes with the TAS, that also we discussed. Then we already discussed the lift force is a result of the pressure differential between the top and the bottom surface. Yes, lift is the pressure differential between the top and the bottom surface. Already we discussed this way, right? This way. An increase in dynamic pressure IS will increase the lift force and vice versa. Yes, we already discussed. An increase in angle of attack will increase the lift force up to 16 degree, we discussed. The center of pressure CP of a cambered airfoil moves forward as the angle of attack increases, we already discussed. The CP of a symmetrical airfoil does not move under the influence of angle of attack, very very important. So for a symmetrical airfoil, CP doesn't change, doesn't move. Throughout the normal range of angle of attack, the aerofoil nose down pitching moment about the aerodynamic center will remain constant. In short, aerodynamic center doesn't change. It is 25% of the chord line. Okay. The lift coefficient CL is the ratio between the lift per wing and the dynamic center. We didn't discuss about CL, lift coefficient. We will discuss in the next chapter in detail. Okay. As the angle of attack increases from -4 degree, the leading edge stagnation points moves from the upper surface around the leading edge of the lower surface. Do you remember what is it says? Already we discussed. Just let me show you, let me take you back here. What it is saying, as the angle of attack is increased, let's say here 0 degree, 4 degree, 8 degree. Okay. Now as the angle of attack increases, this stagnation point here, stagnation point from here, it goes little down, then it goes further down, then it goes further down. So what happens, as the angle of attack increases, the stagnation point from leading edge, it goes below the wing and moves towards the trailing edge, below the wing and moves towards the trailing edge. Okay. Okay, what is it saying? As the angle of attack increases from -4 degree, as the angle of attack increases from -4 degree, the leading edge stagnation points moves from the upper surface around the leading edge towards the lower surface. The greatest positive pressure occurs at the leading edge stagnation point. I told you, leading edge stagnation point is static plus dynamic both, where the relative flow velocity is 0. And okay, I forgot to mention, at the stagnation point here, you see when the molecule comes and stop here, it can neither go up nor go down, you know that. So what is the relative velocity of that molecule? That molecule go and hit, go and hit, go and hit, so it cannot move anywhere. So that's why relative velocity is 0 of that molecule. Okay, imagine, the more you imagine, the more you get more clarity in aerodynamics. Okay, so from pressure drag is the resultant of the pressure differential between the leading edge and the trailing edge of the aerofoil. An increase in dynamic pressure will increase the drag and vice versa. Yes, we know, but we will discuss in the chapter of drag. the coefficient of drag CD is the ratio between the drag per unit area. Okay, when we read the drag chapter, we will discuss in detail. So already now our chapter number 4, subsonic airflow, is complete. Okay, you have to read this chapter, your Oxford book, 2 to 3 times or 4 times, then you will be able to and watch my video, watch these videos at least 2 to 3 times, then all your concepts will be clear. Thank you so much for joining lecture number 2. We will see you in the next lecture, lecture number 3, where we will discuss the next chapter, chapter 5. Thank you so much, and subscribe to the channel.